Everybody who's in credit scoring, hands up? 1, 2, 2.5. Righto. So, let's move right into this.
That means you're safe, you can say almost anything and we'll believe you.
Oh, I do that at work as well. That's fine. Won't be any change. Okay, so let's start off. This is not really an art talk. This is really more a credit scoring talk. But it does describe what I think at least is an interesting analysis that was done with R, and that compared to a lot of standard model building in credit scoring, this has a lot of moving parts compared to the standard sort of thing, which tends to be more or less, let's build a regression model. This has things with many more components. And the point is that doing this would have been very tedious without R, or at least some sort of an equivalent statistical language. So I do reference through this the various bits of R that I use to do the analysis, but I think the interesting point actually is how much you can do with so little R in this particular analysis, because that's what makes this feasible. So this is done in a commercial environment, so we're working under all sorts of external constraints. You've only got 2 weeks to do this job. You can't do things in some particular way. You've got to only build 2 models. We won't let you build 4 models, that sort of thing. So it really is important that you can get a lot done with a little bit of coding. I'm not going to claim that the R code I've used in here is particularly good. It's just what I happened to do at the time, which was a while back. So I'd probably do things a bit differently if I were to repeat the exercise today. But in order for this to make any sense at all, I'm going to have to give you some domain background on credit scoring. The thing about credit scoring is it's about retail finance. So it's people applying for credit cards, home loans, what have you. It's assessing the risk that they will not pay back that loan. So it's very much used in operational systems. So if you think that in Australia there are millions of credit card applications processed every year, it's important that these things be done in as automated a fashion as possible. So credit scoring is what builds the models which go into those systems that make those kinds of automated decisions. And it means it's very much focused on operational issues. It has to be very robust. It has to be capable of being put into old systems that weren't really designed to put up with the kinds of things that you'd want to do if you were unleashing all your statistical tricks on it. One of the things that actually interests me a lot in credit scoring is design issues and the craftsmanship that's involved in building these systems and making all the parts play with each other nicely. Unfortunately, there's not time in the talk today to go into all those. So I'm going to mention 1 or 2, but we'll just say this is what the problem is about, but not go into all the explanation of why it's been done in this particular way. Right. So first of all, it's got that horrible title from nib back here. 3-part title, reject inference, nested conditional models, joint scores. So about half the presentation is just explaining what the title means. So reject inference is basically about predicting what you can't observe. So if you're a lender, you want to make predictions. So you want to know, if I were to give this loan to this person, what's the likelihood that I'll get it paid back or not? So if we're going to reject, and let's take the simple case where the only decision the lender can make is I can give you the loan or I can reject you, so I cannot give you the loan. 2 possible actions that I can take. It's pretty easy to predict the outcome of rejecting an applicant. You've got no chance of losing the money because you haven't lent it to them in the first place, and you can come up with an average cost of having processed them and so on. So there is a cost associated with not lending to a person, but it's not remarkably high. The harder problem is predicting the outcome of accepting an applicant where that applicant is like ones who've been accepted in the past. So it's standard statistical logic. People like you, where you is defined in some particular way, historically have shown this level of performance. Therefore, I will believe the world tomorrow will be the same as the world yesterday, and I'll predict you'll behave like that sort of person in the past. That's easy enough. The hardest part is predicting the outcome of accepting an applicant who looks like ones you've previously rejected. Because if you've rejected people like that in the past, you've got no idea how they would have performed had they actually been accepted. Well, they may have not. So we've got no historical performance information on people who are similar to your current applicant. So what the lender wants to know initially is, what's the predicted outcome if I were to accept absolutely everybody. So then on the basis of that, they can say, well, I can see that this group of people over here is unprofitable if I were to accept them. So in the future, I'll set some sort of a decision boundary. I'll say, people on that side of the boundary, I'll say, no, we're not lending to you. On this side of the boundary, we will lend to you. So the prediction that the lender wants is, what would the world look like if I were to accept absolutely everybody who came through the door? So we have to come up with these predictions, assuming that they've been accepted, and then the lender would set the strategy. So reject inference is this process of trying to make these predictions for a group of people for who, strictly speaking, you don't have any data on how they perform. Now, the generic way of attacking this is to build some sort of a model on the cases with known outcomes. The problem with this, of course, is it's a biased model because you've got censoring of your prior observations, and it's thoroughly systematic because in the past you have done your best to try to reject the people you think are going to perform badly. So it will be a biased model. You try to modify that model based on some knowledge you may have of that censoring process, and then using that modified model to predict what the outcome would be for the censored cases. And the term of art in credit scoring is inference, reject inference. So it's just a prediction. And then once you've got the predicted outcome or imputed outcome for the rejects, you basically pool that data with your known outcome data, then use that whole lot to build the model you actually want to build to make the predictions you want to make for that. So that's reject inference. So when people talk about reject inference, and particularly in the academic literature, they assume this very simplified population flow. So we've got some population of applications coming in through the door, and the lender is taking some action based on the information they can see. So this will be information from the application form or from a credit bureau, whatever. So some portion of those applications they'll accept, they'll reject some. The ones that they reject, there are no further outcomes, that's all you know. Whereas the ones who've been accepted, then depending on how the borrower behaves, they will either end up as a good loan. So once again, this is just term of art. They're called either good or bad. It's not an assessment of the person. It's just shorthand for did they pay it back or not. And then you've got a bad outcome. So that's the simplified population flow. And if I can make this, yes. Okay. So once again, just looking at this reject inference process at a very high level, we're going to build a model of the good-bad outcome on the accepted cases. So that's what's happening here. We've got this population of assets. We can build something like a logistic regression to predict the probability of being good or bad, conditional on you having been accepted. We can also build a model of this censoring process. So with this population of all the applications, we've got these two different outcomes, accepted or rejected. So once again, we can do something like, say, build a logistic regression model to predict the probability that any person coming through the door will end up as an accept or a reject. Then there'll be some mystical process of combining those models. Everybody has their favourite technique. And that's usually interpreted as modifying this model in the light of that model of the censoring process. So we get over, then that gives us this combined model, and then applying that to the rejects over here. So this is taking this combined model, which is somehow a combination of that model and that model, to apply to the reject population to give us the inferred good outcomes and the inferred bad outcomes. Okay, on to the nested conditional models. Okay, in the real world, things are a bit more complex, so we don't just have these standard reject good and bad outcomes. There are typically these multiple nested outcomes and conditional on some parent outcome. So here are the applications coming in through the door, and the lender looks at them and says, okay, these people I'm willing to accept, these people I will reject. I will say, no, sorry, no loan for you. Then the borrower might have been accepted, but they might say, no thanks, I've changed my mind, or no thanks, I've got a better offer elsewhere, whatever you like. So some portion of the accepted applications will be withdrawn by the borrower. Then the rest are taken up. Now then, once they've been taken up, you can end up with these outcomes which is either good or bad. And you can also get various sorts of frauds happening as well. This particular project that this is based on, these were called near frauds, though it wasn't really clear whether they were fraudulent or not. They sort of smelt like fraud, but people weren't willing to say it really was fraud. Now, you can argue that these three outcomes really just all ought to come directly underneath taken up. For various reasons I won't go into, we actually split this up a bit further and said, well, we've got good outcomes and negative outcomes, and then the negative outcomes can be split up even further into a risk bad or a near fraud. So we've got this much more complex structure. So what we're going to do, and what we did do in this project, is we built multiple models. So you can say, let me take the population of applications, and we can build a model that predicts whether they're accepted or rejected. We can take the population of accepted applications and predict the probability of being taken up or withdrawn. For the taken ups, we can predict whether they're good or negative outcome, and for negative outcomes, we can build a model to predict probability of being a risk bad or a fraud. So we're going to take those models, break them down, build them separate models, and then hopefully put them all together again later. So we're going to use those models combined in various ways to try to infer the sizes of those populations in there, which then means we've taken all these rejects and treated them as though they have been accepted and worked out, well, how many of those would have ended up in those various outcome categories. So, just to labour the point, with our taken up withdrawn model, built on the accepts, applied to the rejects, giving us the probabilities of being taken up and withdrawn. Sorry, and this model over here is a modified version of the model developed here. Likewise, with our good and negative outcomes in the taken up, we can build a model of probability of being good and negative outcome, modify it, and apply it over here, and so on. Ditto, last case down here, build a model on the negative outcomes, predicting whether they're risk bad or fraud, and applying a modified version over there. So we can calculate, I mean, the way the diagram has been drawn, it looks as though these are deterministic outcomes, but in fact, the models will be applying are probabilistic models, so we're just predicting the probability of being in various states, but we will end up with probabilities for all these outcomes that we care about, which will obviously correspond to these known outcomes here. What we then do is we take those probabilities and randomly realise them. So for each case, and we're talking tens of thousands of cases, it was rejected, but it will become a good case with probability proportional to the predicted probability of being good. It will become a bad case with probability proportional to the predicted probability of being bad, and so on. So these then end up being deterministic outcomes, but where that outcome is controlled by the predicted probability through all those models we applied. So finally, we're then in a position where we can take the known and the inferred outcomes, pull them together, and then we're in a position where we can build our final model or look at the various strategies we want to apply in decision making. Okay. The last part of the explanation of the title is that we've built, I mean, once again, terminology in credit scoring. Basically, a scorecard is a regression model. It's predicting the probability of some particular outcome, and the scores are the particular predictions. And in this particular project, we had some constraints which meant that we really weren't in a position where we could build a large number of models from the raw predictors. There are typically hundreds of predictors available for building these models. So what we've ended up doing here is we've built two scorecards, one to predict the bad risk, the credit bad risk, the risk of not paying back, and the other one to predict the fraud outcome. And those scorecards are built from the raw predictors, but then in a lot of the models we're building, we're actually just going to use those two scores as the predictors in subsequent models, which then means we don't need to go back rebuilding models for all these other specific models. And this is one way of thinking this, is that it's like a dimensionality reduction on the predictor space. So instead of doing all our models in the space of several hundred raw predictors, a lot of the models we're just doing in the space of these two scores. So all these diagrams down here have the R score on the vertical axis and the N score, which are the risk scores and the near fraud scores on the horizontal axis. And so the aim is to end up with these models which are showing what's the probability of being withdrawn as a function of those two scores, what's the probability of being good as a function of those two scores, and so on. Which then means you can model the profitability, because there are various costs and revenues associated with each of those outcomes. So we can then basically collapse all those together to say what's the profitability as a function of those two scores, and you'll end up with some sort of a tracing a contour line through that and saying, right, anybody on that side of the line, you're unprofitable, we don't want to lend to you. If you're on the other side of that contour line, then you are profitable, we're happy to lend to you. Sorry, obviously I should have said that we've got these multiple independent behavioural dimensions, that's why we need multiple scores. The other is, if you look at these patterns, you can see that there are interactions going on, so we need to consider the two scores jointly in order to make best use of the data. Okay, a little bit of R code, hurrah. I'm going to show you a lot of univariate distributions and some other bits and pieces which are not used directly in the analysis, but which actually shed some light on what's going on. So if we just take one of the scores, this is the risk score. All right, so I've just gone and done the bog standard histogram of the risk score. X-limbs in here are just to set the axes. A lot of the work that's done in here involves comparisons across multiple graphs, so it's important just basically to set the same limits on all the graphs so you can compare them properly. Now, the next one's actually a bit more interesting, because in this one, the number of bins has been chosen by HIST for itself. Here I've asked for 1,000 bins. Just as a matter of history, scores are typically done as integers. So they'll range typically from minus 200 to perhaps, well, you can see up there, maybe 1,200. Scaling is somewhat arbitrary, but these tend to be a log odds scale, so there will typically be a mapping from these scores to a predicted log odds. So if you like, getting a particular score, like a score of 1,000, might mean a particular log odds is being predicted. But these scorecards are not typically using continuous variables. If you've got continuous variables as predictors, they'll normally be broken up into ranges. So age might be broken up into 18 to 25, 26 to 35, and so on. Which means that for each of the predictors going into the model, there's only a small finite number of possible values, which means that overall there's just a specific, you can enumerate all the combinations that those can take up. So you end up with this finite distribution of scores, and some scores, as you can see here, are particularly popular. This has impacts on the usability of these scorecards. So if you wanted to adjust your accept rate slightly, but your threshold was just below that really popular score there, if you changed your threshold to above that score, it means you're going to get maybe a 5% jump in your accept rate. You can't change it in very fine steps necessarily. You'll see the impact of this a bit later on when we start considering joint scores. For this kind of work, you actually would be better off doing everything as continuous variables where popular, so you'd get a much smoother distribution of these scores and you wouldn't get these lumps. Right. Now, we're going to be using scores jointly, and this leads to some problems. We know that the risk bads look pretty similar to the frauds. And if we were just to build two scorecards, one discriminating between good and risk bad, and one between good and fraud, then those scores would be highly correlated with each other. So when we were plotting cases out on that two-dimensional space, you pretty much get a high correlation of the scores, so all the cases would just be distributed near the diagonal. So that would not be much use for setting decision boundaries. So ideally, we'd like to have independent scores so that score matrix is reasonably well filled. So what we did was we did our risk score in a fairly traditional way, just trying to predict good versus risk bad. And this fraud score, the N score, is just discriminating between bads and frauds. And there's possibly some issues with that, but it happened to work out quite well. So I'll show you how that goes. This is the distribution, those two scores. And once again, for those who are not familiar with it, library hex bin, really useful. You can do this kind of two-dimensional histogram. And then so we've just asked it to do a hex bin of N score and R score. We've set the bounds, upper and lower bounds on the score ranges. And we've provided it with some functions here. So these, instead of these breaks being evenly spaced, it's done on a square root scale. You can see we've got this stripe going up here of fairly dense observations, and this one here. Those correspond to particularly popular scores on the N score. So we would have had less clumpiness in there if we'd used continuous predictors throughout the scores. But nonetheless, we've got reasonable coverage over the entire space, so that's not too bad. Okay. Now another problem in this this particular project was we had constraints on the number of models we could build. So rather than building a specific model to predict a specific outcome, instead we build this model to predict that outcome, but we then after the fact see how well it predicts a different outcome and use that instead. Let's skip over the rest of that. It's show you this. Okay, so these, once again, these aren't used directly in the analysis that we really care about. So this is the relationship between the R score, the risk score, and in this case, the outcome here is good versus bad. So this is on a natural log odds scale up here. And this is using the MGCV package, and we're using GAM. So basically, this is a smooth, non-parametric fit in it. It's based on regression splines. A lot of work that's done in credit scoring just tends to assume that this relationship will be linear, but by using GAMs here, we're allowing this to be some arbitrary but smooth curve. So internally, this is basically doing logistic regression, but when we do this up here, what's being set up is a matrix of predictors. So it's rather like doing a polynomial regression, but which uses fewer degrees of freedom to achieve the same degree of smoothness. So just stepping through the R code for the benefit of those who haven't seen this before, we've got a call to GAM, which is nested inside a call to plot. So let's just look at the GAM. Predicting this outcome is equal to G. So everything to the left of the tilde is the outcome, is the dependent variable of the regression. This term to the right is the independent variable, so it's just asking for a smoothing of R score. Family equals binomial makes it the equivalent of you doing logistic regression. Data this. Subset, we're asking for the subset of observations which have an outcome of G or B. So we're trying to model G within the possibilities of G or B. And then the rest of the call down here is the plot, setting limits and setting a title and so on. We would expect that a well-developed scorecard would have a linear relationship between the score and the log odds of the outcome, and that's pretty damn good. The dashed lines, as you expect, are a confidence interval, and these tick marks down here are rug plots. So every tick corresponds to an observation in the data set. So surprise, surprise, we built this model, this score, to predict that outcome, and it does a pretty good job of it. So that's from about -3 to, let's call it +3. So that's about 6 units on a natural log odds scale from the lowest to the highest. So that's how much it's spreading out the, excuse me, the predicted probabilities. Now if we use that same score to predict a different outcome, one that it wasn't developed to predict, in this case we're looking at good versus fraud. And you can see, all right, it's wobbly, but it still wouldn't be too much of a a misuse to say if you were just to fit a straight line through that, there's most of the trend is approximately linear through there. So this risk score does quite a reasonable job at predicting this fraud outcome. And it's about the same degree of separation as on the risk model. So from the risk score's point of view, a bad outcome and a fraud outcome look pretty much equivalent. It does about as good a job at separating either of them from good. So even though it wasn't developed to do that, it does a reasonable job. It's just much rougher and wobblier through the middle. Now, in this case, we're saying, all right, let's look at this risk score. How good a job do you do at separating a bad outcome from a fraud outcome? And the answer is very poorly. If you were to fit a linear curve through that, all right, it wouldn't be completely flat, but still. It's, as far as the risk score is concerned, it can't tell the difference between a bad outcome and a fraud outcome. I should also point out while we're hoppling around in here, one of the really neat things I've dropped off the embedding in the plot. One of the nice things about doing this kind of thing in R is that I've just been able to do all these different graphs just by changing the outcome expression and the subset expression. So I don't have to go off and create different data sets to ask different questions. I can just change that dynamically in the call. So it's basically just fiddling around with those subset expressions and outcome expressions gets me everything I want in here. Okay, now let's look at, this is taken up versus withdrawn. The risk score doesn't do a very good job of that. You can see there's a trend up here, whereas that's flat. So you could say that below a score of, say, 700, there's the lower the score, the slightly more likely you are to be taken up. Or conversely, the slightly less likely you are to withdraw. And that's something that generally occurs in credit scoring as an empirical pattern. The people who are riskier are also the ones who are less likely to wander off and go somewhere else. They're the ones who really want the credit. Not a particularly strong trend there, but that's consistent. Now, let's look at some of the calibrations from the N score. This is the scorecard that was built to distinguish bad from fraudulent. So you can see this does quite a reasonable job of that, although this is now, say, -1 to +3, so that's about 4 log odds units instead of 6. So although this does a good job at separating bad from fraud, it doesn't do as good a job as the R score does at separating good from bad. But these guys are more homogeneous, so that's not surprising. If we look at how well this fraud score does at separating good from bad, from this score's point of view, good and bad look the same. It really can't discriminate between them. And likewise, it really can't make much sense of taken up or withdrawn either. But, we haven't looked at this one before, this is accept versus reject. So you can see that the low end of the fraud score actually corresponds to being more likely to be fraudulent. So the more fraudulent they look, the more likely they are to be accepted in this data set. One possible explanation of that is that if people are actually setting out to commit a fraud, they try to make themselves look attractive. It's a pretty poor fraudster who just manages to get themselves rejected all the time. No harm to anybody, and they really shouldn't be in the business. Okay, now we're getting on to the part which we actually care about, which is the same exercise as before, looking at these calibration curves, but now looking at a bivariate version instead. So here, we're looking at, what's that, accept versus reject. So this is probability of being accepted as a function, as a joint function of those two scores, the risk score and the fraud score. And this one I'm just showing to you because that's a hell of an interesting pattern down there. So this is telling us something about what this particular lender was doing beforehand. They had their criteria set up in such a way that they have this little island of people here who are being accepted quite well. And that's down towards the fraudulent end of the the graph here. Once again, there's some R code up the top. So here, rather than embedding the call to GAM inside the call to plot, I'm splitting it out into bits and pieces. So we've got the call to GAM. We're predicting our outcome, in this case, not equal to R, not equal to reject, where the total subset of outcomes we're interested in is everything. So the opposite of reject is accept. And now it's a smooth of those two variables jointly. And we're storing the result in fit.r. And then later on we can plot that out, which results in this particular plot. So we're saying type response, which means we want it on a probability scale, and we want a contour plot, and so on. So the red area is high probability and higher probability, and the bluish area is lower probability. So you can see that the ones which are low risk, so high on R score, are the ones which were much more likely to be accepted in the past, with the odd exception of these guys. But that does indicate that we really need to have this considered jointly, because we wouldn't have spotted that properly otherwise. Okay, so avoiding the full R and just saying, well, that's basically what we're doing. So now we're looking at bad versus fraud as a function of the two scores. So you can see that the distinction between high probability of bad, high probability of fraud is primarily driven by the risk score, or primarily relates to the risk score, apart from this corner here where it kicks out that way. So if it weren't for these contours kicking out here, you could just have got away with looking at the fraud score by itself. But there is an interaction going on down in this end here. Rightio. Now, given that actually let's go back a step. We can interpret this as a model, because basically you can think of this as a lookup table. For any combination of risk score and fraud score, we can go to the point in here and read off the contours. What's the probability corresponding to that? So there's a predicted probability, which is reflected by those colours and those contours, as a function of those two scores. And any individual case will have its own specific values on those two scores, so it'll have a predicted probability. Let's now check to see how well that predicted probability corresponds to the actual observed outcome, because this has been built on the cases which have actual outcomes. And that's what this is. And this is once again done with a GAM, so that line could have been curved, but I think we'll call that reasonably straight. So that's the predicted log odds, and that's the smoothed actual log odds as a function of that. So that model on the previous slide is doing a pretty good job of summarising the patterns that are in that data. So what we've done up here in the R is we've used the predict function, so we've given it the fit object coming from a previous call to GAM. We've got it to predict the outcome, the probability of the outcome for all the observations that are in our data set. So we're just then storing those predicted probabilities, actually log odds, back into our data frame. And now we're calling GAM again, predicting the actual outcome from the predicted log odds. So doing that sort of thing, close to trivial with R. Okay, now here's a case we saw in the univariate examples before that neither of the scores was particularly good at predicting taken up versus withdrawn. Here's the surface we get from looking at taken up versus withdrawn as a function of those two scores. The vertical scale on this is such that there's really not that much difference between the blue side and the red side here. What are we saying? Taken up is red, yes, okay. So you're more likely to be taken up if you're riskier. And we've also got this more likely to be taken up, well, less likely to be taken up for that little blob there, which probably corresponds to that thing we saw earlier in the accept rates. But strange patterns, it's not actually picking up a lot of variance. And if we do that diagnostic plot that was on the previous slide, we find this. So the relationship between the prediction and the outcome is somewhat challenged. Now, the way we got around that is, I should have said earlier, by the way, that with GAM in the MGCV package, it uses automatic cross-validation process internally to adjust the degrees of freedom of the fit. So you can control how wobbly or not the curve is. And so MGCV divides up the data, builds the model on one half, tests it on the holdout half, repeats that for a number of different values of the parameter which controls the degree of smoothing, chooses a value of that parameter which gives you the best generalisation from the development half to the holdout half. What's happened is, because it's not particularly predictive, effectively it's been overly conservative, it's overly smoothed the data. So this model is smoother than it should be. Although in fact the best thing to do would have been to develop a specific model of being withdrawn or taken up. That's the proper answer, but this being a commercial project we didn't have the budget to do that. So we can, however, increase this magic K parameter up here, allows you to force to change the degrees of freedom of the model. So that basically was forcing GAM to allocate some more degrees of freedom. So instead of being whatever it was before, something like, say, 7 or 8 effective degrees of freedom, that might have boosted it up to maybe 12 or 15 effective degrees of freedom. So it's made it a bit more wobbly. We've still got the bluish areas at the top and the pinkish areas at the bottom, but there's more high frequency content in that. And now if we look at the diagnostic plot for that, okay, it's not linear, but at least it's monotonic. And the other cute thing about this is that we can actually use that curve as a lookup function to correct the predictions. So if we take the original predicted values and then use those to look up the values on this, that will then linearise that curve. So that's basically, we just adjusted that this magic K figure here until this curve became monotonic, and at that point we said, right, stop, enough. Right, okay. Now that we've got all those models, because basically each of those graphs we had before is a model, we now need some way of combining the probabilities, the predicted probabilities for those models. So it's just a little bit of probability of A conditional on B is equal to, etc. Essentially what this translates into is we're doing this multiplicative propagation of predicted probabilities down through that tree of possible outcomes. So, some more R code. Now, before I mentioned that effectively what you want to do is to take a model built on the known data, a model built on the censoring process, combine those somehow or other, and that becomes your adjusted model, which is then used on the data for which you have no outcomes. We have, for this case, done the simplest thing we could come up with, which is basically we're applying a straight adjustment. We're saying if you were rejected, then the log odds for your predicted log odds of being withdrawn should decrease by 0.2. It's just a number we plucked out of the air. Similar thing for good, similar thing for bad. So basically we're saying if you were rejected, then we're going to make the prediction say that you're actually more likely to be bad than the model itself said. Whereas for these other ones, we're saying less likely to be good, less likely to be withdrawn. I won't go through the logic behind that, but these can be made more complex and more realistic. The trouble is you also usually don't have any information to tell you what you should be doing, so we tend to go for the simplest that has some sort of a justification to it. Bit of R code to convert log odds to probabilities, and then we've just got some code like this which is saying here's my data frame D, I'm going to transform that by creating a new variable which is my predicted probability of being withdrawn in scenario A. So we can change these adjustments in different scenarios. So if we're rejected, we're going to do something. Otherwise, we're just going to pick up the predicted probability because it's in the accepted side, so that's our best estimate from the model we've got. So basically, this bit in here is the multiplicative propagation I was talking about before. We do that for the probability of good and the probability of bad and probability of being fraudulent and so on. So that's relatively straightforward and Probably these days I can make that a bit simpler, but all right, it's just a few lines. Then the next thing we have to do, because now we've got for each observation, we have probabilities for the observations which are accepted. We know whether they were good, bad, withdrawn, etc. For the observations which were rejected, we've got predicted probabilities of them being each of those outcomes. So what we're now doing is this little bit of code here is randomly assigning them the outcome with probabilities proportional to the predicted probabilities of those outcomes. So bit of code there and add it into the data frame and convert it back into a factor. Once again, that could probably be made a bit simpler these days too. Which then gets us to the point where everybody, both the accepts and the rejects, has an outcome associated with them. So we can now take that whole data set and we can just predict the probability that you are withdrawn as a function of the two scores. So once again, this is an invocation of GAM, but now where we're using the known and the inferred data in there. So this is predicting withdrawn versus good, bad, and fraudulent as a function of the two. So you can see here, red is more likely. So you're more likely to be withdrawn if you are low risk and if you are low probability of being fraudulent. So the people who are the least bother and the most upright are the ones who are also most likely to take their business elsewhere. Whereas if you're risky, so this area down the bottom here, then you're less likely to withdraw your application, and if you're more likely to be fraudulent, you're also less likely to withdraw your application. And these are now unconditional probabilities in here. Ditto for probability of being good. So the people who are most likely to turn out as good are the ones who are high risk. So low risk, high scores on the risk score, so low risk. Interestingly though, they're also the ones who are most likely to be fraudulent, but from way back at the beginning we said, well, this score doesn't really do a good job at the low risk end. The other thing is, these probabilities here are lower. The probability of being good is lower there, mostly because a higher proportion of these people have withdrawn their business. Because these are all competing outcomes now, G, W, B and N, so if you're more likely to be withdrawn, you're less likely to be all the other things, including good. So that's why the goods are more there than there, because these guys are more likely to withdraw their business. And here we have bad, so this is risk bad, so this is just people who genuinely, non-fraudulently go bad. So they're at the end where they're risky on the risk score, so they're down at the bottom here, and also at the end which is not likely to be fraud, which is pleasing. And our frauds are mostly concentrated down in this corner here, which is looking both risky and likely to be fraudulent. So as I was saying earlier on, all those last four slides can now be pulled together. You can assign weights to those different outcomes and you can get a display that looks like this that says what's the expected profitability as a function of those two scores, and draw a decision line through there. So, from an R user group perspective, I think the thing is that we've done an awful lot of work there with not too many pages of R code to do it, which is actually important in the commercial world. I mean, when I went away and did this analysis, I might have done, say, 100 pages worth of work, but a lot of that is paranoia and testing out ideas and checking to see that the probabilities do actually add up to 1 at any given point, that sort of thing. But once you actually have established that it's all doing approximately what you think it's doing, the heart of the matter is actually quite small in terms of the R code that was required to do that. So that, I think, is the important point out of all that. And it's got pretty pictures, which is awesome.